Well, dear students, this time I am again meeting you in this lecture. I welcome you. This linear differential equations with constant coefficients. It is lecture number 13. We have already delivered up to this up to 12th this lecture. Up to 12th lecture, we have discussed some rules for finding out the what is called this particular integral. Different rules for finding out particular integral. Now today I want to give you the method how to find out the particular integral when we can express sine or cos in terms of exponential function. Particular integral when to express sine x or cos x as exponential function. Let me just introduce. If your differential equation is like this, say it is f of dy is equal to x square cos 2x. I have already given you the method how to find the particular integral when this independent variable is linear, that is xv form. This is not here xv form. This can be now quadratic, this can be cubic. Now you can express this cos 2x as exponential. How? You know that cos 2x is actually it is a real part of e raised power iota 2x. How it is? When you write e raised power iota 2x, what is this? It is cos 2x plus iota sine 2x. Isn't this? What is this cos 2x? It is the real part. So this implies a real part of e raised power iota 2x is your cos 2x. Suppose if it would have been x square sine 2x, in that case you would write sine 2x is your imaginary part of what? E raised power iota 2x, because when we open e raised power iota 2x, it is cos 2x plus iota sine 2x. What is the imaginary part here? It is sine 2x. So this way you can have the right hand side is now. Let me share some example. Let us solve one differential equation here. Suppose we want to solve. Let us solve the linear differential equation with constant coefficient. Suppose we want to solve simple equation d square minus 1y is equal to x square. Say it is cos x. I will take x square cos x. First of all, what you do is you write it is auxiliary equation. What is auxiliary equation? As usual, it is d square minus 1 equal to 0. This gives d square is equal to 1, which gives your d is equal to plus minus 1. So what is complementary function in this case? c1 e raised power minus x plus c2 e raised power x. You will say this is your complementary function. What is particular integral? Particular integral, you write your particular integral is now it is x square cos x by d square minus 1. Now this is not linear here. You have previous method, perhaps the fourth rule or fifth rule that I have given you, when we have the right hand side of the form x v, where v is function of x, it can be cos sine, and this is linear, but here it is not linear. How I go? I will convert this cos x as the exponential. I will write this is actually a real part of this x square e raised power iota x by d square minus 1, because when you open e raised power iota x, actually e raised power iota x, you write e raised power iota x is your cos x plus iota sin x. what is the real part of e raised power iota x? That is your cos x. So this cos x is here real part of this. Now we will apply the previous method, perhaps the third one, when it has exponential. I will write it. It is real part of e raised power iota x will go out as usual, as in case of exponential function, when you have right side x times e raised power ax, this form, then what you do is you have here f of d, you write this e raised power ax out, then x by f of d plus a, then this f gets increased by what? A. Similarly is the case here. This e raised power iota x will go here. This is your x square by this is your d. What is your a? Iota. It will be d plus iota square minus 1. Please just revise that part where we have evaluated x e raised power ax form. Right side capital X. Any function of x, e raised power ax. E raised power ax, say it is cos x, whatever it is. We take e raised power x out, then d gets increased by the power of this. It is iota here. At that time that was a, now it is iota. This will be d plus iota. Now we open it. What is this? It will be your real part of e raised power iota x. This is x square by this is d square plus iota square plus twice iota d minus 1. This is your real part of e raised power iota x. This is x square by d square, then iota square is minus 1 plus 2 iota d minus 1. This we can write well, this is the particular integral. Particular integral is, it is rp आपको साथ साथ लिखना है, real part e raised power iota x, then x square by it is minus 2 plus d square plus iota d. D minus 2 d square plus 2 iota d. It is 2, sorry. It is 2 iota d. It is here 2 d iota. This 2 d iota. Now what you do here, you remember we want to convert this because our numerator is now, this is the algebraic expression. In case of algebraic expression, we take the help of binomial theorem. For that we take here the lowest power of d common. It is here minus 2 into d raised power 0. So lowest power of d is here minus 2. Take it out. You will write it. It is your real part of e raised power iota x square. Let us take minus 2 common. This will be 1 plus d square plus 2 d iota by minus 2. This you can write further. It is a real part of, it is e raised power iota x by minus 2 out. This is your x square by 1 plus, now it is minus 1 minus d square plus 2 d iota by 2. Be cautious here. Now I shall find the particular integral in the same way. Well, this is the particular integral. It is a real part of e raised power iota x by minus 2. This is your 1 minus d square plus 2d iota by 2 raised power minus 1 into x square. Now we have to open it by binomial theorem. You know how we open it by binomial theorem. It is equal to a real part of e raised power iota x by minus 2. Why real part of? Because our right hand side involved cos x. Well, open this. It is 1 plus d square plus 2d iota by 2. Then it will plus d square plus 2d iota by 2 square plus so on. I will not write cube here because my highest power of x is 2. I have given you the description. When we have x raised power m, we open it by binomial theorem up to powers of d raised to power m. You know it. Well, this is equal to a real part of minus e raised power iota x by 2 into it is 1 plus d square plus 2d iota by 2. When you open this, what is this? It is d4. This will be 4 d square iota square, then plus 4 iota d cube by 4 plus so on. I have to omit here this d4 I don't need, and d cube I don't need. I have to omit them because you know d of x square you have 2x. When you find d2 of x square, that is 2. D cube of x square, it is 0. So from d cube and onwards we have the derivatives of x square 0. Therefore we omit or leave d cube and higher powers. Higher powers means after d cube, d4, d5, d6, we omit them. Therefore we are left with, now we are finding out what? A real part of minus e raised power iota x by 2. This is 1 plus d square plus 2d iota by 2. Then you are left with only, it is iota square minus 4d square by 4 into x square. You have to leave d cube and d4. Well, this is equal to a real part of minus e raised power iota x by 2. Take this x square here. This is now x square plus d2 of x square, then 2 iota d of x square by 2, then minus d2 of x square when we operate with x square. Well, it is equal to a real part of minus e raised power iota x by 2 x square plus, what is d2 of x square? You have just seen d of x square means 2x. d2 of x square is simply 2. It is 2 plus 2 iota, what is d of x square? It is 2x by 2, then d2 of it is minus 2, second derivative of x square. This gives you a real part minus e raised power iota x by 2. 2 gets cancelled here. It is only x square plus 1 plus 2 gets cancelled. It is iota x. 2 iota x, sorry. 2 iota, because it is 2 2s are 4. 2 gets cancelled. It is 1 plus 2x iota, 2 iota x minus 2. Okay? Yes. Now you can write it, it is a real part of minus real part of, right here minus 1 by 2, open now, e raised power iota x cos x plus iota sin x into x square. This is minus 2 plus 1, it is minus 1, then plus 2x iota. Now here you have to find out the real part by multiplication. That will be your complete particular integral. Complete particular integral. You see how we go? It is equal to real part. I will now directly write down the real part. This minus 1 by 2 will be there. It will be with both real and imaginary because it is the multiple 1 by minus 1 by 2. When we multiply this cos x with x square, it is free from iota, so it is real part. Write it x square cos x, a real part. Multiply cos x with minus 1, yes, it is real part, minus cos x. Multiply cos x with this, it will be 2x cos x iota. I have to drop it because I need a real part. I drop iota sign. Okay, this I don't need. Multiply with iota sin x x square, iota x square, drop it because it is imaginary. Multiply this with this, drop it, it is imaginary. Multiply this with this, it is 2x sin x iota square. Iota square is minus 1, so this will be minus 2x sin x. This is the real part. When I multiply this with this, imaginary, this with this, imaginary, this with this, it is real because it involves iota square. So accordingly, it is the real part of this is, so particular, now you will write particular integral is, it is minus 1 by 2, you can write it, it is x square minus 1 cos x minus 2x sin x, or you can write in simplified form minus 1 by 2 x square minus 1 cos x, it is plus x sin x. Minus minus is plus x sin x. So this is your particular integral. Therefore, what is now complete solution there? You will write down the complete solution. The complete solution is y equal to complementary function plus, but it is y is equal to c1 e raised power minus x plus c2 e raised power x, then plus minus 1 by 2 this part x square minus 1 cos x, x square minus 1 cos x, then plus x sin x. This is the complete solution of this differential equation when you have right hand side not involving function. Suppose you have now questions like this, you can do it. Suppose you have f of dy is equal to, say it is x cube cos x cube sin 2x. You want to convert this, when you find out particular integral, you want to convert this into what? This exponential function, because this is not your linear. So when you find out particular integral, you will write it is imaginary part. Here at the end you have to take the coefficient of iota, imaginary part. Imaginary part of what? X cube e raised power iota 2x. Okay, because when you open it, it is cos 2x plus iota sin 2x, and when you open it, it involves the cos 2x plus sin 2x. I need sin 2x, that is imaginary part, by f of d. Now you have the coefficient of x here 2 iota, it gets added by this, this comes out, and finally you have to take the imaginary part. So this is how you solve the differential equations. When right hand side has some x, powers of x not linear, then function of sine, cos, extra. With this I think we have concluded the all types of this this finding out the what is known as particular integral. In this way we complete. Now we come to very important concept. It is homogeneous, Cauchy-Euler homogeneous linear differential equation. Linear differential equation, homogeneous linear differential equations, which are also known as Cauchy linear homogeneous differential equation. Let me introduce this, and we will be doing with that this. Now we introduce homogeneous linear differential equations. Homogeneous. This is also known as Cauchy-Euler. Cauchy-Euler homogeneous linear homogeneous differential equations. Let me have the introduction. The differential equation actually, this differential equation is a homogeneous, known as Cauchy-Euler. This will not be now with constant quotients. We have to now develop the method how to reduce this with constant coefficients, linear differential equation with constant coefficients, so that we can solve it by previous methods, the methods that we have already done. You see how we go. We have the differential equation of the form it is x raised to power n dny dxn plus a1 x raised to power n minus 1 dn minus y dx n minus 1 plus a2 x raised to power n minus 2 dn minus 2y dxn minus 2 plus so on to plus a n minus 1 x dy by dx plus a and y is equal to x. This is called the Cauchy-Euler homogeneous linear differential equation. You see what happens here. You have the highest power of x here, n. What is the order of the derivative? It is also n. Order, I mean. It is the nth order differential equation with degree 1. That is why it is known as linear differential equation. Linear. Why the name linear comes? Because degree is 1. Do you follow me? xn dny dxn. This is some constant here, a1. Then x raised power n minus 1, here order dn minus 1. X raised power n minus dn minus 2. This coincides with this. Here x raised power 1 dy by dx. The power of x, the order of this derivative. The power of x n minus 2, the order of derivative n minus. The power of x n minus 1, the order of the derivative n. This is the what. But here we take the constant here from here. You can take it here. You can have here also constant. It is a non-zero constant. Because it is 0, then this term will not survive. So constant can be here. If it is a constant here, we can divide by this, so we can reduce it into only n constants. Otherwise it will have n plus 1 constants, where ai running from 1 to so on to n are constants. Right side is x and capital X is function of x. This is some function of x. This differential equation first is called homogeneous linear differential equation. Homogeneous linear differential equation. The form is Cauchy-Euler. Cauchy-Euler method. Cauchy-Euler. You have understood, you have come to know how we recognize this. You have here x cube d3y by dx, x square d2y by dx, x dy by dx. You will be coming across differential equations like this, where you have constants. Constants may start with this, and we have started with this because it starts with this. We can divide by that and get the constants and constants. Okay. Now our aim is to reduce this differential equation into one, again known as linear differential equation with constant coefficients. To reduce, it is method of solution. To solve equation 1, that is this equation 1, we reduce it to linear differential equation with constant coefficients. Linear differential equation with constant coefficients. For that, we have a suitable solution. We use a suitable solution here. The suitable solution for that is the suitable substitution. Substitution that we use. The suitable substitution that we use is, we take x is equal to e raised to power z. We put x is equal to what? E raised power z. So when we solve such equations, we will be to solve this method of solution is we put x is equal to e raised to power z. This implies log x is z, which implies z is log x. If we differentiate with respect to x, this is dz by dx is 1 by x. You see. Now I want to find out, now I have dy by dx. I can write dy by dz by dx. What is this? It is chain rule, as you know. Why I use this? Because I have involved z here. I have dz by dx. I can write it now further. It is dy by dz. What is dy by dz? And dz by dx is your 1 by x. Therefore, I am getting dy by dx now 1 by x dy by dz. Then I will write here this setup. This setup will imply me, if I multiply by both sides x, this will give me x dy by dx is dy by dz. If I denote here, put d by dz, I will denote it by capital D. But remember that my d by dz is here capital D. So what is x dy by dx? It is my dy. What is my d? D by dz. Therefore, in the given equation, I have the term there. You have seen equation number 1, I have there x dy by dx, that I can replace now by dy. You see what happens, the variable coefficients are not now involved here, variable coefficients go away. Now I differentiate this, again with respect to x. Just a minute, we shall first attend the azan. Now what we do is we differentiate this again with respect to x. We will go on differentiating this with respect to x. This will be your differentiation of dy by dx with respect to x is derivative of 1 by x dy by dz with respect to x. Here you can use the product rule. It is derivative of 1 by x with respect to x, second function dy by dz as it is, then plus 1 by x as it is, derivative of dy by dz with respect to x. I have using here the product rule. This is your d2y by dx square. Be cautious. Derivative of 1 by x with respect to x is minus 1 by x square. This is your dy by dz. This is plus 1 by x. Now here I will use the chain rule because it is the with respect to z, it is independent variable z. I will write here derivative of dy by dz with respect to z into dz by dx, because I need the derivative of dy by dz with respect to z, only then it is d2y by dz square. But when we differentiate this with respect to x, we use chain rule with respect to z, dz by dx. This setup is here. So after this you get d2y by dx square is your minus 1 by x square dy by dz. This is plus 1 by x. What is your d? It is d2y by dz square, but dz by dx is your 1 by x. So this is d2y dx square is equal to, I can take 1 by x square out because this is 1 by x square, this is also 1 by x, 1 by x, 1 by x square. This is minus dy by dz. This is your plus d2y by dz square. Okay. Now if I take this z x square here, this is x square d2y by dx square will be equal to, now minus d by dz is d, this is plus d square into y, because your d is now d by dz. So there in the given equation I have the term x square d2y by dx square. I replace that by this. What is this? It is x square d2y by dx square will be equal to d into d minus 1y, where your d is d by dz, that d. Similarly you can write now, similarly when we differentiate this again, similarly we get x cube d3y dx cube. What is that? It will be d into d minus 1 then d minus 2y. Okay, and so on. If you have, when you have x raised to power n, d and y dxn, what is that? It is d into d minus 1, d minus 2, d minus 3, that so on to, it will be d minus n plus 1, because you see you have here d minus 2, it is actually d minus 3 plus 1, this 3. Here you have d4. It is d minus 2 plus 1. So it is d minus n plus 1 into y. So we replace these values there. So by this, the given differential equation gets converted into differential equation with constant coefficients. By using these values in first, when you use these values in first, the given homogeneous, in fact it is Euler Cauchy-Euler equation, Cauchy-Euler will get transformed now. It will get transformed by the substitution, transformed into linear differential equation with constant coefficients. Okay, when we use these values, x raised power n dny dxn, by this x cube d3y by dx cube, by this x square, we use it in the given equation. You don't have there the x cube, x square, x4 terms. It will be now the linear differential equation with constant coefficients. So what is the suitable substitution when we want to reduce Cauchy-Euler homogeneous equation into one which is with constant coefficients? The suitable substitution is the independent variable involved in the differential equation, that is x. We put that x e raised power z, not necessarily z. You can put x is equal to e raised power t, e raised power theta, so on. By that way you can go, but there if you put x is equal to e raised power theta, your d by d theta will be capital D. And by next lecture we will be taking some questions on this, which will be now of the type Cauchy-Euler homogeneous linear differential equations. I have given you the method how to solve them, how to transform those equations into linear differential equations with constant coefficients. Thank you very much. We will see you in next lecture. Thank you. Till then, wait.